Greetings. Welcome to today's class. So let's continue from where we left off yesterday. So if we recall, in yesterday's class, in the previous class, we are looking at so-called steady state cornering, right? So wherein we assumed addition to V and constant, we also assumed that the radius of turn is also a constant. The maneuver or the scenario that we are considering in steady state cornering is that like a car is going straight and then like we take a turn and we allow the transient effects to settle down, and then we look at what happens to the steady state motion as the vehicle moves in an arc of constant radius. So considering that the radius of turn is very much higher than the wheelbase of the vehicle, we derived a simple expression for the steering angle delta, which was L by R plus alpha F minus alpha R. And then we applied the equations of motion for translation along the lateral direction and also rotation. That gave us a couple of equations, and we substituted for alpha F and alpha R, assuming small slip angles, and then like we got an expression for delta as L by R plus KV Vx squared by RG. So we got the same expression for the understeer gradient through this derivation. Okay, so this is where we stop. Okay. So in today's class, we are going to build on this. So before we go ahead, any questions? Okay. So let's continue from here. So let's start analyzing this equation. Okay. So please note that we are considering steady state motion, right? So let me once again reiterate the scenario. So I'm writing it again and again so that like we remember this scenario that we are considering. So we are considering a scenario where vehicle is taking a steady turn. Okay, it's taking a steady turn on a curve of constant radius r. So that is the maneuver that we are considering. So given this, let us now plot what will be the variation of the steering angle delta. This is the vehicle longitudinal speed, okay, based on this particular equation. So let's plot it. Okay, so let us do this. So we plot Vx on the x-axis and delta on the y-axis, right? And let's say this is the origin. So we are essentially plotting this, and then like let's analyze what happens for various cases. Okay, so that's what we are doing. So we are going to consider this equation delta equals L by R plus KD Vx squared by RG. Okay, so that is the equation we are going to consider. So the first case, we consider the case of understeer. So people will abbreviate it as US. Okay. So as we know, here the understeer gradient is positive, KV is greater than 0. So immediately, if we look at this particular equation, we can immediately observe that as Vx increases, the steering angle required to take the same turn increases. So that is something which we need to remember. Please note, we are essentially with a turn of the same radius or constant radius r. Okay, so we can immediately observe that as Vx increases, okay, as the longitudinal speed increases or the vehicle travels faster and faster, so what's going to happen is that like the value of delta, value of the steering angle required to take the same turn of radius r, required take the same turn of radius r, okay, a given radius r increases. Okay, so this is something which is very, very important. Okay, so that should be kept in mind, right? Okay, so is the first case, right, of understeer. Then let's consider neutral steer. So what happens in neutral steer? Let's say we abbreviate it as NS. Okay. So in neutral steer condition, we know that KV is going to be equal to 0. When KV is exactly equal to 0, we can immediately observe that delta is going to be equal to L by R. That's it, right? So it is always a constant for any particular value of speed, right? So if I substitute KV equals 0 in that above equation, we see that the second term on the right hand side of the equation vanishes. So consequently, we are only left with delta equals L by R. Okay, so that is something which we can readily understand from the condition of neutral steer. And when we have oversteer, okay, abbreviated as OS. So when we have an oversteer condition, as we know, under oversteer, KV is going to be less than 0. So essentially what happens is that as Vx increases, the value of delta, which is required for taking the same turn, as Vx increases in value, delta decreases, goes down. Okay, so this sort of like counterintuitive, right? So isn't it? But that's a characteristic of an oversteered vehicle. Okay, so that is the property of an oversteered. Okay, so these observations are important. So please note what is the scenario that we are considering. Okay, so we are considering a scenario where we are having a turn of constant radius, and then like we are essentially looking at what happens when the value of Vx changes, right? So this curve, which I have plotted, is for neutral steer, okay? And this particular steering angle is L by R, okay? So the value of the steering angle always remains at L by R for a neutral steer vehicle, okay? For an understeer vehicle, it increases with square of speed, right? So this is how it is for an understeer vehicle. Okay, so when Vx is 0, all the curves will start from L by R, right? So as is evident from that above expression. And for an oversteer vehicle, let me use, let's say, green color, right? So for an oversteer vehicle, it will go like this, and then like it will hit this 0 speed at the critical speed. Okay, so we have already derived the expression for the critical speed Vxcr, as if we recall from the previous class, it was square root of Lg divided by modulus of K. Okay, so this is something which we have already derived. Okay, so what it physically means is that like when we hit the critical speed, the even a small perturbation may make the vehicle spin out of control. Okay, so that is the bottom. Okay, so these are the three characteristics curves. Okay, for delta versus Vx for traversing the arc of the same radius R. All right. So this is one way to interpret the condition or state of understeer, neutral steer, and oversteer. Okay. And for an understeer vehicle, there is another term important, which becomes important. For an understeer vehicle, the term characteristic speed is used to denote the speed at which the steering angle doubles from the 0 value, the y-intercept. Okay, so what does it mean? So if we look at the 0 intercept of this curve, it's L by R, right? So the characteristic speed is the speed at which the steering angle becomes 2L by R, okay, at which delta is equal to twice the y-intercept, okay, which is L by R. So if we substitute it in this equation, okay, so what happens? We will get L by R is equal to L by R plus have kV Vx squared by R, right? So kV, now Vx I just replace by Vx characteristic, okay, just to denote the characteristic speed divided by R. So if we simplify this equation, the characteristic speed expression comes out to be this, So we can see that it is going to be LG divided by KV. So at first glance, one may think, oh, okay, this looks very similar to the critical speed. But then please note that the term characteristic speed is defined for an understeered vehicle, whereas the critical speed is defined for an oversteered vehicle. So the physics itself is different. Okay, although as a formula, the expression may appear the same. Okay, so that is something we need to keep in mind. Okay, so once again, please note that the term characteristic speed is applicable for understeered vehicles. Okay, so that's something we need to keep in mind. All right. Okay, so this is one way of interpretation. So we will go to another way of interpreting the characteristics of understeer, neutral steer, and oversteer by considering curvature behavior. And I'm sure this is one curve which maybe all of us would have also frequently encountered, like when people talk about these three states, okay, understeer, neutral steer, and oversteer. So what is this situation? Let us say we consider a curve of radius r. Okay, so I'm essentially considering a curve of radius r. Okay, so this radius is r. Okay. All right. Okay. So now let's consider a vehicle, a four-wheel vehicle traveling. Okay. So let us say I'm just drawing a diagram. So this, okay. So, and let's say we have a four-wheel vehicle which is traversing on this, and then like it's taking the turn, okay, on this curve, right? So we have four wheels. Sorry. Let me just complete the drawing. All right. Okay. So we have these. What is this four-wheel vehicle which is going like this, right? So now, let us say, like we have delta to be constant. Okay. So we give the same steering angle. So that's where we are looking at curvature response. So now we are looking at what will be the radius of the turn with change in speed when the same steering angle input is given. Previously, we were looking at the steering response, right? So what will happen to the steering angle as speed is changed to traverse the curve of same radius r, right? That was this characteristic. Now what we are saying is that like we will always give the same delta steering angle. What happens to the radius of turn when the vehicle speed changes? That is the question we are going to ask ourselves. Okay. So curvature, please note that is reciprocal of radius. Okay. So that's something which we need to remember. So recall that the steady state behavior is given by delta equal to L divided by R plus KV Vx squared divided by Rg. Okay, so this is the standard expression we will be using again and again. So this implies that I can always rewrite this equation to be the following: R equal to L plus KV Vx squared by Rg divided by delta. Okay, so this is how I will rewrite it. And we consider the case where delta is held as constant. All right, so let's see what happens. So now, if we consider understeer, okay, as a first case, let's consider the case of understeer. And as we already know, KV is greater than 0. So please note the denominator delta is held constant. Okay, so the denominator delta is held constant, right? So what happens as P is increased? So we can see that since KV is greater than 0, as Vx increases in value, okay? Yes, please.
Sir, in R is equal to that, R will come again in that derivation.
Oh, okay. Sorry. Yeah, sorry. This should be Vx squared by G. Thanks for pointing. That's a typo
Sir,
from my
so,
end. Yeah.
So one more thing, so characteristic speed. So what's the importance of the speed, and why we are saying that it is only applicable for understeer vehicle?
So that is a definition because you can see that other characters, other states will never reach to L by R. Okay. So it is essentially the speed at which the steering input for taking the same turn will reach twice the value at the zero speed. So there is a significance of it. We will see it later. Okay, as we go. Okay.
Oh, okay, sir.
Yeah, thanks for pointing it out. Yeah, please delete that R from that formula, that came by mistake. So for understeer, since kV is greater than 0, as Vx increases, as the speed increases, we can immediately see that the radius of the turn increases. Okay, so this is why we would have seen one usual representation of an understeer vehicle where if we have a road, we will always show an understeer vehicle going out of the turn, right? So we will do a representation like this, So it is just to show that, like compared to the desired radius, an understeered vehicle, because since kV is greater than 0, it is always going to go out of the turn unless otherwise I change the value of delta. Suppose if I adjust the value of delta to be L by R, okay, for traversing a curve of radius R, my understeer vehicle will not go on an arc of radius R. Okay, so that is the meaning, okay, of this. That's how we should interpret this curvature. All right. So now, if we consider a neutral steer vehicle, so what will happen? As we know, kV is equal to 0. So this implies that anyway, R is constant, right? R becomes equal to L by delta. So we can see that it's independent of the speed. So this curve corresponds to a neutral steer vehicle. Okay, so this curve corresponds to an understeer vehicle. So this is the usual diagram which we would be typically exposed to, right? So when we talk about these three states, and if we consider an oversteer vehicle, what happens when we consider an oversteer vehicle when kV is less than 0? So what happens is that as Vx increases, the value of R is going to drop, right? So from the expression that we have written down, it's very clear that when if kV is negative, the radius of turn, right, for the same steering angle input reduces. Okay, this is for an oversteer. Okay, so please note in all these things, the steering angle delta is kept constant. Okay, so that's something which is very important. Okay, so we keep the same steering angle, and suppose we have a path of radius r, which is L by delta. We have an understeer vehicle and the speed increases. What happens is that like speed keeps on increasing, the what to say, the radius of turn increases, right? And the vehicle seems to be going out of the turn. So for a neutral steer, it will always stay on the curve. For an oversteer vehicle, as speed increases, the radius of the turn decreases. So consequently, the vehicle seems to go into the turn. Okay, so that is those are the three scenarios. All right. So I hope this diagram is also clear. Okay, so this is the curvature response. So we have looked at this concept of understeer, neutral steer, and oversteer from two different perspectives. Okay. So now, any questions before we go forward? So now, let us go and look at it from the perspective of our systems perspective. Okay, so essentially, if we recall, we spent quite some time looking at dynamic systems in general, and then like trying to characterize them through input output models and so on, right? So let's look at it from that perspective. So let us say we essentially want to characterize the cornering dynamics. Okay, so we essentially want to look at the vehicle when it's cornering. Okay, so my system, so to speak, is the vehicle undergoing a cornering motion. So I'm interested in characterizing vehicle cornering dynamics. Okay, so this is what is my interest. Now, if this is my interest, so what happens is that we know that the input to the system, right, from a dynamic systems perspective, is going to be the steering angle. So the steering angle is going to be the input, and there can be multiple outputs, okay, depending on our what to say visualization. We could have yaw rate as one, okay. We could also have lateral acceleration as another output, okay. We could also have curvature, okay, as a. So depending on our essentially visualization or outlook, we are going to have different characteristics, okay, that we are going to study. So that's what we are going to do, right? So once again, let us consider the steady state response to a given steering angle. Okay, so that's what we're going to consider. So let me set the context once again. So let us consider. Yes, any questions? Someone seems to be unmuted. Okay, thanks. So let us consider the steady state response to a steering angle. Okay, so that's what we are going to do. Now, let's figure out what are the important parameters that one needs to consider and what are the corresponding so-called gains. So if you recall, when we dealt with transfer functions also, when the output reaches steady state, the ratio of the output by the input, right, at steady state, we call it as the steady state gain, right? So essentially, let's look at various measures, right, or metrics to characterize this. Okay, so first let's look at what is called as yaw velocity gain. So let's look at yaw velocity gain. Okay, and what happens is that if we look at this, the yaw velocity gain g subscript yaw is defined as the steady state yaw rate divided by the steering angle input. Please note, once again, from a general dynamic systems perspective, the term gain is used to denote the ratio of the output by the input, right? When there is a what to say when the vehicle has reached steady state, right? So that's what has happened, right? So we have psi dot s divided by delta. Now, what is the steady state yaw rate? The steady state yaw rate is going to be equal to Px by R, okay? That is going to be the steady state yaw rate, divided by delta is going to be equal to L by R, and just substituting the formula for delta, right? L by R plus Kv times Vx squared by R. Okay, so this is a standard formula. Okay, so if we simplify this, we are going to get Vx divided by L plus Kv Vx squared divided by G. Okay, so this is what we will have as the yaw velocity gain. So if we plot this yaw velocity gain for as a function of Vx, okay, for different state of steer, let's see what happens. Okay, so I'm plotting the yaw velocity gain G subscript yaw as a function of Vx. So for neutral steer, it's very easy to visualize, right? For neutral steer, what will happen? Kv will become 0. So the yaw velocity gain will be Vx by L, right? So what will happen? When we plot it with respect to Vx, it's going to be a straight line with a slope of 1 by L, right? So this is what will happen for neutral steer. I'm sure all of us can immediately agree, right? So for neutral steer, the yaw velocity gain will be just Vx by L. I hope this is clear, right? So anyway, it's going to be in that manner, right? So we are essentially taking the neutral steer condition as an example. Of course, if I'm looking at the yaw response, obviously I want the yaw velocity gain to be more, right? So yaw velocity gain being more, that means that, like I'm going to reach essentially a turn, right? Or go into a turn much faster, right? So essentially yaw velocity gain being higher is more meaningful to me. However, like if we look at the oversteer vehicle, what will happen is that the yaw velocity gain will be much higher than the understeer vehicle, but there is a problem, right? As we go closer and closer to the characteristic speed, asymptotically, yaw velocity gain will go to infinity. Okay, and that is something which is undesirable, right? So this is a limitation with an oversteer. And if we consider an understeer vehicle, what happens is that like an understeer vehicle essentially will be like this. And this is where characteristic speed comes in. At Vx equals Vx characteristic speed, the yaw velocity gain will reach the maximum, okay? And then it will start reducing, okay? So you can essentially show this, okay? So I hope now one viewpoint of the characteristic speed or one impact of the characteristic speed becomes clear, okay? So you could try it out. You can essentially see that, you have the characteristics, the yaw velocity gain flattening, like as the slope of the yaw velocity gain versus Vx becoming equal to 0 at the characteristics. Okay, so please do try this out. All right. So this is the characteristic of the yaw velocity gain as we. Okay, I think I should be a bit careful here, but anyway. So this is the what to say variation or like of
Sir,
the yaw. I'm sorry, what is it? Yeah.
sir, this VX here will correct. Is this two red and these two lines are same representation, or are they different?
Which ones?
V red color VX CR and VX and character.
The VX here is a red. I use red color.
Yeah.
VX characteristics, I have used a purple color, right? So yeah.
Okay. Will it be like a same representation, or are they different?
Same presentation means I didn't understand. No? Like so, V critical is it is what it is, right? Vx critical,
Yeah,
right?
yeah,
I
correct.
just that is square root of LG by KB, right? This V
Yeah.
characteristics is also like the square root of LG by KB, but KB will be different, right, in magnitude. So it's only a relative
Okay.
position, right?
Okay. Okay. Yeah.
So,
Okay.
so please note that KV is understeered gradient, but the magnitude can be different. So, okay. Yeah.
Okay, sir.
So of course,
Yeah.
depending on that, V characteristics, Vx characteristic can be to the left of V critical also. May be possible, right? Depending on the value of KV that you're choosing for a particular condition, right?
Okay, sir.
Okay. Yeah. Okay.
Yeah.
Fine. Okay. So that is the yaw velocity. All right. So once again, we can see the trade-off, right? So see, we get stability, but at the expense of performance, right? If we go for understeer. So now we can understand why most passenger cars are understeered, because we want stability, right? So, but then like they are a little bit sluggish, right? So, but that's okay, but on the other hand, if you look at what to say, race cars, like we want performance, right? We want higher yaw rate gain, yaw velocity gain, and so on, right? So consequently, we go for performance, but then like we need to be careful, right? So we need to ensure that we operate within the critical stream. Okay, so that's something which we need to be careful of. All right. Okay. So the second parameter is what is called as lateral acceleration gain. So what is this lateral acceleration gain? Let's say we call it as GC. It is going to be the steady state lateral acceleration normalized with respect to G units. So typically accelerations are normalized with respect to G units in units. And then like we divide it by the steering angle, okay, delta. So then we divide by the steering angle input delta. So as we know, the steady state lateral acceleration is going to be v squared by r, right? So vx squared by rg, that is the steady state lateral acceleration, and then like we divide it by the usual expression L by R plus kV Vx squared divided by Rg. Okay, so this is what we have. So then what we have the acceleration gain V equal to Vx squared divided by Lg plus Kv times Vx. Okay, so that's what we. Okay, so this is how the expression will come in. So if I now do a similar plot for the lateral acceleration gain, once again, we are going to plot it with respect to Vx. So now if I plot the lateral acceleration gain for a neutral steer vehicle, please note that even for a neutral steer, the relationship is going to be like Vx squared, right? So this is going to go something like this. So this is going to be for neutral steer. So this is going to be a quadratic relationship, okay? And once again, like if I can just this, right? So this is my critical speed. Okay, once again, this is just a demonstration or a qualitative graph, okay, just to show where the critical speed is. And once again, for an oversteered vehicle, the acceleration gain is going to be higher than other types, but then like same story, right? So as we reach the critical speed, asymptotically, the over acceleration gain goes to infinity. And if we look at the understeer vehicle, what is going to happen in the case of an understeer vehicle is going to be, it's going to be a bit sluggish, right? So there's going to be something. Okay, so this is how an understeer vehicle's acceleration gain will look like. Okay, so these are the characteristics as far as acceleration gains. So same philosophy, right? So as far as concept wise is concerned, we are having a trade-off in performance when we are looking for stability, right, with an understeer. So then people also look at curvature gain. So once again, this characterizes the curvature. So you consider the curvature gain GCUR. Okay, so as we discussed, the curvature is a reciprocal of the radius. So it's going to be 1 by R. And the input is anyway delta. Okay, so that's what we have. So we have 1 by R in the numerator, and delta is going to be equal to L divided by R plus KV Vx squared divided by Rg. Okay, so this is what we have. And consequently, we are going to have G divided by GL KV Vx squared. Okay, so this is what you end up with. Okay, so for the curvature. So if we were to draw a plot for the curvature gain versus the speed, right, the longitudinal speed, what will we get? Okay, so let's look at that for all the three states. So we are plotting Vx versus the curvature. So for neutral steer, once again, Kv is 0. So immediately we will see that the curvature gain will be 1 by L, okay, for a neutral steer. So this will be 1 by L for a neutral steer vehicle. All right. So the curvature gain remains the same with respect to speed for a neutral steer vehicle. All right. So now what will happen to understeer and oversteer? So once again, if we consider the oversteered case, so if this is the critical speed, so what's going to happen? Just like the other two gains, as the speed approaches the critical speed, we are going to go to infinity. Okay, so it is going to go something like this for an oversteer. So it will start with 1 by L, and then it will go asymptotically to. Okay, so this will be the oversteer case. And for neutral steer, as we already have seen, for understeer, as we already seen, it's going to be sluggish. So essentially, it's going to go something like this. Okay, so this is going to be case for understeer. Okay, so these are the three gains for that essentially characterizes the response of like oversteer, neutral steer, and understeer conditions, right? So that's something which we need to remember. So once again, the bottom line is that like understeer vehicles are stable, but then like it comes with a sacrifice or compromise or trade-off in performance. So that's something which we need to remember. All right. Okay. So any questions?
Sir, the oversteer behavior over here, like as if the KV is less than 1, right?
KV is less than 0.
Oh, okay. Less than
Yeah,
0.
less
Understood.
than
Sorry.
0. Yeah.
Okay.
Yeah. So once again, understeer means KV is greater than 0. Neutral steer means KV is exactly equal to 0. Oversteer means KV is less than 0. Okay, so those are okay. So essentially, these are some characteristics. So what I will do is that like maybe this is a good place to stop today. And in the next class, I will look at testing of steady state handling characteristics and also like look at objective evaluation of cornering response. Okay, so that's something we will look in the next class. And then like, but then like even the testing of steady state handling characteristics, we will sort of like derive metrics and look at some characteristics based on the steady state relationship that we have derived. Okay. So, any questions before I close today's session?
Sir, we saw the like the relation between Vx and the understeer oversteer tendency, but sir, like this KV is dependent upon weight distribution and cornering stiffness. Is it also possible to establish a relationship between front axle slip angle and rear axle slip angle and oversteer understeer behavior?
So yes, so because you can immediately see that, see the sign of KV is related to alpha F minus alpha R, right? So if I go up, see what is this delta? Delta is L by R plus alpha F minus alpha R, right? Is it not? So let
Yes,
me
sir.
write that. Okay, so okay, it's here, right? So we can immediately see that we have this equation, right? So delta is equal to alpha F minus alpha, right? So this equation is already available to us. So we can immediately observe that if I equate those two equations, alpha F minus alpha R is in fact equal to KV Px squared by Rg, right? Is it not? Right?
Okay.
So that's what we have processed. So immediately you see a connection between the slip angles at the front and the rear with respect to the three conditions, right? See, if we have an understeer condition, KV is positive, right? What does it mean? Alpha F is greater than alpha, okay? So,
Yeah.
so that's a good point. I forgot to state that. Thank you for raising that question. So in understeer, the front wheel is going to slip more than the rear wheel, okay, while taking a turn. Slip angle, okay? Yeah, that's what.
Yes.
Okay, yeah. When KV is equal to 0 in neutral steer, alpha F is equal to alpha, okay?
Alpha.
And in oversteer, alpha F is less than alpha. Okay, that means that the slip angle at the front will be less than the slip angle at the rear. Okay, so one could interpret that way also. Yeah, good point. Thanks for bringing it up.
Thank you, sir.
Any other questions before we close today's session? Okay, so if not, let me stop the recording. Thank you.